This lesson's about uniform circular motion, centripetal acceleration, and centripetal force. Now, circular motion is motion that traces out the circumference of a circle. And uniform circular motion means that the object is moving at a constant speed. Speed is constant. So let's say it's going around the circle at a constant speed of 5 meters per second. However, velocity is still changing. Remember, velocity is a vector. It has both magnitude and direction, and the object's velocity is changing as it goes around the circle. At the top, let's say it's moving with an instantaneous velocity that's in that direction, right? Because it's tangential to the circle. At the side, it would be moving down like that. That would be its instantaneous velocity, would be downwards. And so its velocity is always changing. And because velocity is changing and acceleration is the rate of change of velocity, circular motion always involves acceleration. It can be tempting to think that because the object is moving at a constant speed, there's no acceleration. But remember that velocity is a vector. So here's our object, and it's moving around in a circle, and I'm drawing its instantaneous velocity at these 4 points. Let's imagine that what we're doing is we're spinning an object in a horizontal circle at the end of a string. So the other end of the string is here, and the string is in that direction. If I were to cut the string at this moment when the object is at the top of the circle as I've drawn it here, it would keep going in a straight line out like that. If I were to cut the string when the object were here, it would keep going down like this. Remember, Newton's first law tells us that if there's no force acting on an object, it's going to keep going in a straight line. So the string is pulling on the object and keeping it from going in a straight line. It's bringing it in towards the center. So the string is accelerating the object in this direction. The acceleration is inwards when the velocity here is perpendicular to that, is tangential. So we've got a tangential velocity and an inwards acceleration. And in fact, the acceleration at all of these points points towards the center. That's what keeps the object from going off tangent to the circle. So the acceleration is always pointing to the center and pulling the object around the curve. And we call that the centripetal acceleration. The acceleration that keeps the object on that circular path is directed towards the center, and it's called the centripetal acceleration. Centripetal meaning center seeking. Now you can show that if the tangential speed is v and the radius of the circle is r, then the centripetal acceleration is equal to v squared over r. We could write that as v sub t, but we also often just write it as v. V squared over r gives us our centripetal acceleration. Now also remember that the tangential speed and the angular speed are related by this relationship, and so we can take the above and solve for another equation. The centripetal acceleration is equal to v squared over r. The tangential speed is equal to r times the angular velocity. That's still squared, so we've replaced v with our omega over r, and that gives us omega squared r. By the way, just a note that I've written centripetal acceleration as a sub r. R stands for radial because it's the acceleration in the radial or the in direction. You might also see it written as a sub c, c for centripetal. We can carry on from there and make another substitution to get a third equation. The centripetal acceleration, which is equal to the angular speed squared times the radius, gives us this. Remember that the angular speed is equal to 2 pi over the period. We go 2 pi radians in one period, and that's squared. So this is my omega multiplied by r, and solving there, simplifying, I get 4 pi squared times r over the period squared. So just another relationship that we can use. Let's do a practice question. Find the centripetal acceleration of a yo-yo that's being rotated horizontally on a frictionless surface at the end of a 0.75 meter string if it makes 3 revolutions per second. So here we're asked to find the centripetal acceleration. And based on what we're being given, here we've got the radius, and here we've got actually the frequency being 1 over the period. I'm going to use a variation on this equation. So the centripetal acceleration is equal to 4 pi squared times r over t squared, but t is equal to 1 over f, rearranging here. So this becomes 4 pi squared times r times f squared. And now all I have to do is plug in. I get 4 pi squared times 0.75 meters multiplied by 3.00 hertz, and that's squared. Remember that hertz is the same as seconds to the -1, so when I square that I get seconds to the -2, and multiplying through here I get meters per second squared, which is the units that I would want for acceleration. Well, if I do that multiplication, I get approximately 266.48, or rounding to two significant figures, 270 meters per second squared. So there's an example of using one of our equations. Now, we've hinted at this already when talking about the string, but Newton's first law says that if there's no net external force acting on an object, it's going to continue moving with its existing velocity. But we want the velocity to keep changing in circular motion. So there's got to be a net force that's doing that, that's acting on the object, pointing towards the center of the circle in the direction that we've said the centripetal acceleration is, in order to provide that centripetal acceleration to change the direction. And not surprisingly, we call the net force the centripetal force. And we can solve for an expression for it just by using Newton's second law. The centripetal force is just equal to the mass times the centripetal acceleration. So, for example, mv squared over r, or m times omega squared r. Now just be cautious that the centripetal force is not a new force. It's just a sum of other forces, and we give it that name to indicate that they're pointing in towards the center of the circle. That sum of other forces is pointing in towards the center of the circle and causing circular motion. So it's not a new or special kind of different force. It's just a combination of other forces pointing in towards the center of the circle. And that net force can be provided by a combination of various different things. It could be provided by tension, for example, if you're swinging an object on a string. It could be provided by gravity, for example, in the case of a satellite orbiting the Earth. It could be provided by friction in the case of a car moving around a curve on a road, the friction keeping it from skidding. Or it could be the normal force, for example, in the case of a roller coaster going around a loop-de-loop, and the normal force pointing upwards in towards the center. Again, so it's not a new force, it's just a sum of other forces. Also notice, because the centripetal force is always perpendicular to the direction the object's moving, it can't do any work on the object, and therefore it can't change the speed of the object. Remember that if the object is moving with velocity like this, then the centripetal force is acting like that. And from our relationship for work, which is equal to our change in energy, is equal to the force times the displacement times the cosine of the angle in between them. And that angle is always 90 degrees. So the centripetal force is not doing any work on the object. Let's do one example problem to finish. We have a 900 kilogram car trying to make a turn of radius 40 meters. We're asked to find the maximum speed at which it can do that without skidding if the coefficient of static friction is 0.55. Now the first thing you might ask is, why are we interested in static friction if we're talking about something moving? And that's because the tires are not actually sliding with respect to the ground. The bottom of the tire is momentarily stationary with respect to the ground if it's rolling without slipping, and so we need to think about static friction. So friction here is going to provide the centripetal force. So the relationship is that the centripetal force is equal to mass times the linear speed squared over the radius of the turn. And if we want to find the maximal speed that we could have, let's solve for the speed, and that's going to be equal to the square root of whatever the centripetal force is multiplied by the radius of the turn divided by the mass of the car. Well, we need to know what's the maximal centripetal force we could provide in order to solve for the maximal linear speed that the car could achieve and still negotiate the turn. Well, what's providing that centripetal force? The force of static friction. So the centripetal force is equal to Fs max. At least the maximal centripetal force is equal to Fs max. And Fs max is equal to the coefficient of static friction multiplied by the normal force. And the normal force, because this is an object moving on a flat plane, on a horizontal surface, the normal force is equal to mg. So now what we do is we take our centripetal force, our maximal centripetal force, and we plug it in there. So the maximal speed will happen when we get the maximal centripetal force, and that's equal to coefficient of static friction times m times g times r divided by m. And notice that masses actually cancel, and so the 900 kilograms is not important to the question, and we'd get the same solution no matter what the mass of the car was. So we get that the maximal speed is equal to mu s, our coefficient of static friction, times acceleration due to gravity times the radius of the turn. And plugging in, we get 0.55 multiplied by 9.81 meters per second squared, multiplied by 40 meters, and then square rooted. And that gives us approximately 14.7 meters per second. And putting that in kilometers per hour and rounding to two significant digits, we get approximately 53 kilometers per hour. So that's the maximal speed that the car could be taking and still negotiate this turn. So that's an introduction to uniform circular motion, centripetal acceleration, and centripetal force.